Guys, we're on day 6, last day of this unit. Woo woo! This is my favorite day. All of Unit 5, optimization. So we get to do lots of problems with context, and you kind of see most of this unit hasn't been conceptual yet. It's just like, do this, do this, do this. And so now we actually get to apply it and see how all these derivatives and what we've been doing can relate to things, okay? Okay. So I'm going to go ahead and actually answer this essential question with you, the process that I like to do for optimization, okay? But first thing I'm going to do is I'm going to get my equation. Then I'm going to make any manipulations to the equations to try to get it down to 2 variables. Substitution, whatever we need. Then I'm going to make sure I know my feasible domain. If we're in production, we can't produce a negative amount, okay? So we're going to look at that domain. And then I want to use AP writing here, okay, for justification with the first or the second derivative. So make sure we really, really get those, okay? All right, so let's look at this first one. 2 positive numbers whose product is 192, and the sum of the first plus 3 times the second is a minimum. Okay, so I want to find. I'm going to give my 2 positive numbers, I'm just going to call them x and y. And we know that their product is 192. And my domain, I already know that they are positive, so both of these have to be greater than 0. And then it says the sum of the first plus 3 times the second, and that is what I am looking to minimize. Okay, well, I've got this into 3 different variables, which isn't good. So I need to get this into 2. So I'm going to use, since this is the formula that I want, okay, it's kind of like step 1, I'm going to use this to plug into one of these 2. So I can see that x is 192 over y. Okay, so now this is, I'm going to go ahead and rewrite that so that we can rewrite as the power rule so I can find my derivative. So I've already done my feasible domain of knowing that they're both positive. So I'm going to get my derivative. And I'm looking for where this is going to be equal to 0 or DNE. And a lot of people mess up here, okay? So be really careful. I'm going to go ahead and get this into a common denominator. Okay, so I'm going to multiply top and bottom here by y squared over y squared. So now I have my derivative. So my critical numbers that I'm going to look for where the first derivative is either 0 or DNE. So I'm going to look at where this guy is equal to 0 or where this guy is equal to 0. And if you don't get this common denominator, you'll lose this a lot of times, okay? And you won't get the critical number part right. Um, 192 over 8, 64. So square root is plus or minus 8. And then that's 0. So I actually have 3 critical numbers, and a lot of times people lose points there. They don't find all of them, but there are 3. So now I'm going to go ahead and find what I need to with those. Well, the only one I'm looking at is 8 because I know that those guys are not in my domain. My feasible domain has to be greater than 0. So those are out. So I really just need to look and see what's happening here. So at 8, let's pick like 1 and 9 and plug them into the first derivative. So I got out a negative and a positive for my first derivative, which means f is decreasing and increasing. Thank goodness, because we were looking for a minimum. And if we didn't get negative to positive, then we wouldn't have got a minimum. But wait, we've only shown a relative minimum because if all I say is that f prime goes from negative to positive at x equals 8, that only tells me that I have a relative min at x equals 8. And I don't want a relative min, I want the absolute min because it said, where is it a minimum, right? So how do I show that that's the absolute? Well, this is a special case. So since this goes from negative to positive and it is the only critical value in our domain, okay? Then I know, since it's the only critical number and it's going from negative to positive, that it has to be the absolute minimum. Okay? So then we can go plug in and find what our other one is. Oh, I put X's, but we were doing Y's. I'm so sorry. Those are Y's. Okay, so that was my Y. So now I can go plug in what X was. Remember when we plugged X was 192 over Y. And that is 24. So we have to make sure, this is a lot of times missed, okay, by just saying, oh, f prime went from negative to positive, therefore it's the max or the min. Sorry. No. Okay, you have to add in that extra step. The only critical number. Otherwise, you've only shown that it's a relative. Okay. Here is production costs. And is there a production level that minimizes average cost? So average cost is this guy over x. Well, let's go ahead and rewrite that. Okay. And so it's already step 1 and 2 are already done. I've got the equation and it's only in terms of x and c. So I'm going to go ahead and get my derivative. Oh, my domain. X is units produced. So x has to be greater than 0 because we can't have a negative production. I guess it could equal 0. That would be silly. Okay. So c prime, 2x minus 6. So my critical number here is at 3. This is where I talk about, I almost always do the number line, but look at how nice and easy the second derivative is. It is always 2. So c double prime of 3 is greater than 0 because it's 2. So I'm going to use my second derivative test here. Okay. So that tells me that I have a relative min at x equals 3. So how do I make it an absolute min? So we say, and since x equals 3 is the only critical number in our domain, there is an absolute min at x equals 3 now. Okay, so then it says, well, if you can find it, what is it? Okay, well, let's go find it. So plug in 3 into your C here. And that was that x squared minus 6x plus 15. And see what you get out. And remember, this is in thousands. So it would be 6,000. Okay, let's do another one. So many fun ones. I don't think which ones I want to do in class. We'll go ahead and do this one together. Okay. A rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular corrals. All right, so they are adjacent. What dimensions should each coral be so that the enclosed area will be a max? So if I have 200 feet of fencing, what is the fencing actually? It is the perimeter. Okay, so how do I find the perimeter? Well, I know that this is like the same variable, and then I'm going to go ahead and give this whole length a variable. So the 200 will have to count, in this case, for twice the y plus 3 times the x. So that has to give me a total length of 200. And then they want the enclosed area to be a maximum. So my area is x times y. 3 variables, blah, blah, blah. So we need to solve for one of these and plug it in. I'm going to go ahead and solve for y. Okay, so I'm going to plug that in. And go ahead, I'm going to simplify so I can take an easy derivative here. And let's see, I know that x and y both have to be greater than 0. But I also know, let's see, they're going to have to be less than a certain number as well. So if x was 200 divided by 3, it would have to be less than that. And y would have to be less than 200 divided by 2. Or we won't have any room for the other ways. Okay, so now I'm going to go ahead and take my derivative. And I got my critical value to be 100 over 3. And again, this one might just be easier to take your second derivative and plug it in. That is a negative. I mean, it's always a negative no matter what. So if it's a super easy second derivative, the second derivative test is really nice. Okay, so since I have this guy, and x equals 100 over 3 is the only critical number in our domain, then there must be an absolute max at x equals 100 over 3. Okay, so what dimensions should each coral be so that the enclosed area would be a maximum? So I know I have my x equals 100 over 3. Let's go find what y would be. Negative 3 halves times 100 over 3 plus 100 So 50, but that was for the whole. I want for each of them. That y was all of it, so split that in two, and I get 25. So 25 feet by 100 over 3 feet. Give you the max area that you could have. And I think that's super cool to know if you're a farmer or something, you want to try to get the most area for your little piggies to run around in. Okay, we're gonna do number 4 together in class. I like that one. And let's see. Let's go do an AP classroom. We'll try to get through the oil leaking in class. Let's go do this one right here. This one's not too bad. It's got some E's just to review. Just wants the absolute minimum value. So I'm going to take my first derivative, and I want to make sure you can do that. Do you see the product rule? First times the derivative of the second plus the second times the derivative of the first. And then I'm going to go ahead and factor out what I can. So there are no D and E's, only 0. E to the 2x times 2 could never equal 0. So my only critical number is negative 1/2. Okay, so let's see. Do you want to use the number line with negative 1/2? That wouldn't be too bad, using what, negative 1 and 1, so plugging those into this derivative. So I know this part's always positive, so if I plug in a negative 1 over here, so plugging in a negative 1 would give me negative, plugging in a 1 would give me positive, which means f goes from decreasing to increasing. Now, we also have to state for an absolute max that this was the only critical number. So f prime goes from negative to positive at x equals negative 1/2, and x equals negative 1/2 is the only critical number. Therefore, there is an absolute max at x equals negative 1/2, and the y value, because it wants the value now, be careful, so I have to go plug that in. So 2 times negative 1/2 e to the 2 times negative 1/2. Simplify if you want. I got negative 1 over e, but you do not have to. Okay? Okay. So just a few more. If you'd like to try some, I have a ton of examples and we're going to be working through some, but try to get through some in class as well. But that's what I have for today with us for notes. I'll see you in class. Good job.